thank all of you even more for having me and for inviting me along. It's been a very, very interesting 4 days for me already, 3.5 days. And it'll get even more interesting, hopefully, in the breakouts in this afternoon. I had a very, very nice lead up by this urban session before, because I will re-emphasize some of the things that have been said, and I'll bring another lens to it. And essentially I'm saying infrastructure has been shown up in all the talks before as very important, as co-shaping what is going on. And our group in Oxford is just taking it one step further and saying, okay, why don't we start with infrastructure and then see how the other things evolve around it. My 3 main messages, short and crisp and communicative. Infrastructure systems provide the link between the climate modeling, between the natural world modeling and the socioeconomic systems, both in terms of how we can model them, but of course also in the real world, they facilitate all the interactions that are important. And the second part of my talk I will spend on pushing forward the acknowledgement and the proper recognition, again, both in modeling and in how we describe the system, of complexity. Again, complexity was a word that came up a lot of times in the presentations, and people have talked about how the new generation of integrated assessment models are taking into account more of the complexities of the system that they are describing. And I make the case that actually there is even more out there in terms of methodology that we should take into account. And a very personal note at the end is that information and evolution-centered conceptualizations are providing methods that we could use to derive dynamics for those complex systems. That's my personal journey. Very humble compared to some of the journeys that I have heard about so far. Just because I'm rather new to the business, I started studying physics for 5 years straight in the German system. I have a knack for nice buildings, so that's the University of Potsdam. Then I did a PhD at the Potsdam Institute in Ottmar Edenhofer's group, and with Elmar Kriegler being my direct day-to-day supervisor. And then I moved to Oxford for a postdoc and now for a research fellowship, which allows me to do my own work as long as I bring in more money than I cost, which is the usual arrangement. Yes. Originally, I was very interested in information, in quantum information theory, to be honest, and I was interested in it because it was the enigmatic world of quantum mechanics to understand. It was more this, am I able to really understand it? That was the challenge. And they say it's also, you make something useful or practical at the same time. Unfortunately, after I convinced myself that yes, I can do it, I found out that actually less than 500 people in the world are actually interested in it, and the practical application is so far away in the future that it's not really practical. But at the same time, fortunately, climate change came ahead as a big thing in Germany. It got hyped in 2006 and 2007, and the Potsdam Institute was next door, essentially. So I ended up in the working group 3, shaped around IPCC language in Potsdam, and did a PhD on what Michael Hahnemann was talking about, the irreversibility economics and the role of uncertainty and learning in the aggregate DICE class, and a bit more complex, but the DICE plus class, you should say, of integrated assessment models, and what, for example, how the flexibility of the mitigation effort determines the value of new information that could come in. How much would we value new information depending on how fast we can act upon it, and where are windows of opportunity, and how inert are the systems actually that we need to change, our emission systems. I then continued to my postdoc on a big project led by Jim Hall in Oxford. It's a flagship project in the UK, bringing together 5 different sectors of infrastructure, transport, water, energy, waste and ICT, and trying to build an integrated model to capture all those interdependencies that we've been hearing on, that those different systems put a demand on one another, and that it functionally depends on one another. So both in risk terms and in standard operation terms, we need to integrate those systems. And this is what this big project has been done from 2011 and is still ongoing, and I'm still half-time involved in that.
What is ICT?
ICT, sorry, information computation technology, that's that short ICT. On the side, I've been working with Miles Allen in Oxford on continuing my work on climate parameters, uncertainties, and how you can learn from data about it. And we've wrote a few papers around why people shouldn't focus on climate sensitivity so much. And I've been contributing to the TCR chapter in the IPCC report. But that has been a sideline which I have been fortunately enough to be allowed pursuing by Jim, my main supervisor. So that's me. So pretty much a theorist turned modeler. The first degree was in physics, the second degree was in economics. Now I'm somewhere in system science, complex systems. So that's me in a sense. And so when I continue talking about this, the things and why infrastructure matters and why complexity matters, I'm always interested in, first of all, do we have the right methods? Do we have the right tools to talk about these things? How can we develop our tools forward? And then, of course, secondarily, to apply them to solve problems. But that's not my main drive. That's another purpose. And the second question for me then is, how does information play in all these fields? Because that's still my primary intellectual interest. What the role of information, all of these things, in the form of uncertainty, in the form of different people having different information, strategic interactions, and all the other aspects of it. So this is a rather old build picture of the human environmental system. Interesting for me is that the human component is rather small and in the middle of it, and the sophistication in the modeling increased very much around it. And I would still argue that our understanding of how this part in the middle, A, looks like right now, and B, changes over time, is very, very limited. And so this is where I would want to spend my time on improving it. And if that works, we've seen that before, and I'm very, very, and I'm very, how should I say, this is the state of the art, I would argue, and it's also very good to see all those pieces in there. And I would want to focus on one particular piece. Here it is down there, human settlement and infrastructure. And for me, this would actually be a network connecting most of the other things that are over here. And if we used it like that, if we used infrastructure systems as a connecting entity, you could unify many of the other bubbles in here in hopefully a very useful way, both methodologically and also conceptually. So how can we do that? For me, first of all, I mean, this is the infrastructure system. The infrastructure system is not a small bubble amongst many other bubbles. For me, this is the infrastructure system. And of course, part of it only, North America. And of course, only part of it because we only see the light. We don't see what happens when it's dark. But we already see that it doesn't follow the usual spatial structure that we would apply to a climate model. It doesn't happen in boxes, it happens in networks. And it happens in networks that are hierarchical. It happens in networks that have particular structures at particular scales. So the tools we would use to partition space into structure space when we want to talk about infrastructure will be different than those when we talk about fundamental physics, which always happen with nearest neighbor interactions and never happen with actions across long distance. Of course, that depends on timescales. Let me switch forward. One problem we have in our infrastructure project when we try to model it for the UK only, national scale, is that no one actually knows what infrastructure is. And that's not special. That's not special to infrastructure. That's right for many other terms that are being used. But it is important in one particular sense that if I say, let's put infrastructure at the center of what we're doing, then I will have a definition of infrastructure that would allow us to do that. And usually, this is what people think about infrastructure. It's big, lumpy stuff stuck in the ground. It's roads and rail and you know, this is one particular characterization. The lack of a functional definition of infrastructure that would actually be working like, okay, if I look at something, I can use this definition to say whether it is in or out. And we don't have anything that is satisfying in that way. There's another nice one. That's the high judge talking about pornography, saying I can't define it, but I know it when I see it. And this is what we apply to infrastructure, and which is we have a particular. we have a particular set of characteristics. We know it's the stuff that is long in gestation and lifetime. It comes with contractual problems. It comes with economic network effects, and it is foundational for other services that the society needs. So there are a few hints at what infrastructure is. We have a working definition in our project, the Infrastructure Transitions Research Consortium, for anyone who's interested. We say it's a network of assets operated to providing foundational services for the functioning of the economy. Okay, but that's just another version that doesn't really tell you. And so the situation we are in is that we just end up with lists. Everyone lists things that is infrastructure. And you can have your list, I can have my list, and they look different, and different things are in or out. But one of the longer lists I could come up with is this one, and it's not mine, it's one of my colleagues, Raghav Pant, who's also in Oxford. So this is all the things that we consider infrastructure. And if I'm interested in urban systems, and I have figured out all of these, I'm pretty much there. There is, of course, the whole thing of socioeconomic things, there is the demographics, and there is the impact of all of this on the rest of the economy. But if I had understood how these things work and change over time, I have made a big step. So that's why infrastructure is important. That's what I already said. Natural systems work fine in fields. Infrastructure systems work fine as hierarchical networks. That's the electricity network of the UK in 3 hierarchy levels. The other thing, of course, infrastructure is the originator of our impact on the environment. That's trivial, but it's also the place where the impacts occur and accumulate. And this is to say that infrastructure, just the other continent, is not just one network, it's many networks, and it is services that depend on one another. And so if you ask, for example, what depends on electricity, sewage depends on electricity, telecom depends on electricity, water depends on electricity, so on, so on, so on. And if you have a good grasp on what all those assets are doing, you can then start doing the disruption events, you can start doing the impact assessments, the vulnerability assessments. That's not new, and we've heard about it before, and that's kind of where I would leave the status quo. We can use very sophisticated understanding of infrastructure networks to talk about indirect effects of natural hazards. And we always find that the indirect effects are far greater than the direct effects. So it's not just people living within hazardous areas that is important, it's actually people affected by not having the services that infrastructure systems will provide in those areas. And those are the big effects of natural hazards, not just people being there when something happens. Is which services we can no longer get. And so this is the methodology. We use the natural science fields. We have a good understanding of our networks. We take in the demographics, and then we can come up with losses and indirect losses. So the second half, or rather the last 3 minutes of my talk, and I actually will stretch it a little bit, hopefully. I mean, 20, is about my own personal interest, because all the rest so far is kind of state of the art. Some people are doing it, other people are doing parts of it. But what we really are not getting from this is how the system changes. We only get a good understanding of the current system. We don't get an understanding of how the system changes over time. And we have to acknowledge, so this is just a network as it is, and we want to know how this network changes, not just the operation of the network, but the network itself, its topology, its structure, its functionality. This is the information backbone, the internet backbone, and this is how economists still in many places understand economic growth as a fitting exercise of a three parametric function. You take labor, you take capital, and you take maybe energy, and then you fit your GDP. So you don't have any procedural, any functional understanding of how the economy actually works to come up with macroeconomic projections. Complexity, why we need it, and what it really means instead of just more complicated, nonlinear, coupled dynamics. It means that the system we're talking about is made up of many components. Check, that's true for the socio-technical economic system. It is self-organizing, it has reflective downward causation, which means that it's not just cause and effect as in a physical system, but it means that the emergent properties of many things happening on the micro level then work back. So single individuals all work together to vote for a government, and then this institution affects their own behavior backwards. So we have reflective downward causation. We have those systems evolving over time, not simulated by a fixed set of dynamic equations where the initial conditions and the forcing will get you the future, but evolving by increasing complexity over time in a way that is intractable and fundamentally intractable, which means that the physicists would say that the possible phase space, or the number of states in the phase space, increases faster than we have time to actually go through the phase space. So the law of big numbers doesn't hold anymore in these systems, and we can no longer simulate them efficiently. And which is one of the most important things, these systems, and if infrastructure is one of them, will require multiple formalisms to understand them fully. We cannot represent a complex adaptive system with a non-complex adaptive formalism, and even not with a single other complex adaptive formalism. Which means ecologies of models are good, many different formalisms are good, which is why also I'm saying do not only start with infrastructure, but fine, start with urbanism as well, start with worldviews, start with climate models, put all of them together, but not in a make one out of many, but evolve your basis, your ecology of models to understand that system. And they are value and emotion loaded, which doesn't make it easier. The systems also have limited controllability. So if we want to manage infrastructure systems, we cannot assume that we can just build what we want. We have to investigate where the control nodes are and what we can do about them. And the possibility of projection and planning is limited, we should change the way we manage them. We should not expect our governing bodies to make right decisions, because they cannot make right decisions in a system like that. When they cannot have perfect foresight, or not even enough foresight to make robust decisions properly, we should expect them to fail. I mean, the financial world knows that. The investors, they assume to be wrong in 90% of the cases. For our governments, the only reason why it still works is that we exchange them every 4 years. So they can make errors, and then we exchange them, and then the next troop can make their errors again. That's okay. But why do we expect them to be right in the first place? So we need to fail more graciously. That's the message here. And it directly falls out of acknowledging that the system we're dealing with is complex. So, and as I'm out of time, I will close by saying that there is a huge range of different fields that comes together that have to say something about how these systems do evolve and do develop. And I have taken that as a challenge we talked about educating people, and we talked about learning about different fields. Those are all the fields I have started reading about, and I have dived into and talked to people in those fields, because all of them have reinvented complexity many times. They have invented different formalisms, different conceptualizations, and there is no complexity science yet. There is many attempts to it, and for me it's an incredible challenge to bring that into the mainstream and to try and take the essence of it and incorporate it into integrated assessment. Thank you very much.
Talk. Thank you. We have time for a couple of questions. Igor, Ian, why don't you start to come up?
So I fully agree. The question is how you do that. Can you give like a little bit insight?
Yes. Unfortunately, I lost 5 of my slides to time. I have worked with colleagues at the TU Delft, Igor Nikolic and others. They are coming from industrial ecology, and they apply agent-based modeling to simulate the co-evolution of the institutions and of the physical system that shape, for example, choices around a harbor project or a city motorway or things. And there you can start, that's the computational sociology or the computational idea of that institutions are purpose system as are technologies. And once you apply that unifying framework, you can throw lots of computation power at it. And then you can say, okay, I go to the ground, I try to understand what my agents are doing, and then I can explore the space of possible dynamics. I can never go back to prediction, but I can explore spaces of more realistic dynamics than I could with a simulation framework.
Sherry?
Yes, I'm curious if you feel like we're doing enough in our curriculum, particularly at the advanced levels, in regards to complexity. It seems like it's a really important dimension, and I know from teaching in undergraduates and graduates that we don't do many courses.
Physicists don't learn about it, and economists have to stretch themselves to learn about it as well. So no, we don't, is the simple answer. And the problem is that, as I said, it has been invented in many fields. So there is computer science's way of doing it. There's the whole ecology world that has invented it and has talked about it. And as it hasn't come together to build a single field yet, you wouldn't even know where to start to put it into a curriculum. So I think that for the time being, it has to be left as advanced specialist courses for a whole range of different students. Could be mathematicians, could be statisticians. They all could take a course in complex systems, and they would understand it, and they could do something with it.
Great. So last one.
Could be just a one-word answer, Alexander. Does growing complexity generally yield less likelihood to fail or more likelihood to fail of any given infrastructure system?
Wow.
That's one word.
If I answered that question, I would be non-credible. So
What's your take on it? You're a theoretical physicist. So the theoretical physicist in you wants to offer an answer.
As well.
can, yeah. I mean, more complexity leads to less efficiency, but to more robustness.
Oh, there. I appreciate that answer.
But that's not generally true. But there are.
That's great. Give an answer and then say, oh, by the way.
Great.